Okay, in our last video, we talked about the difference between shells, subshells, and orbitals. And what I've got over here is an example diagram of what a 4 or an n equals 4 shell would look like. So let's just put this in our notes. We'll say example for n equals 4 shell. Okay, and let's kind of walk through what's going on in this picture. And let's start from big and work our way to small. So the first thing outlining here is the shell. And basically what the shell is it's the overall picture of this energy level. So it's saying within this energy level, we've got different subshells within them. So let's identify what a subshell would be. So a subshell in this example would be basically anything residing within a certain energy level. So for example, this subshell that I've highlighted right here is made up of d orbitals. And if you remember, there are 5 different d orbitals. We saw the picture of that. They kind of look like funky clovers. They're really hard to draw, so oftentimes chemists will just simplify these using boxes or circles. And then, like we said, the individual orbitals are just called atomic orbitals or orbitals. So for example, down here, it's saying that the orbital for a p orbital is made up of 3 different p orbitals. They kind of look like this. So one goes up and down, one goes side to side, and one essentially goes in and out. I'm not going to bother drawing the x, y, and z axis, but I just wanted to indicate that there's going to be a py, a px, and then a pz orbital, meaning we've got directionality. So we can fit 2 electrons into any one particular atomic orbital. So in this case, we can fit 2 electrons in this one, 2 electrons in this one, 2 electrons in this one, for a net total, or max, of 6 electrons. So this is the max that can fit. All right, so this is the overall idea of a shell, is we can fit 2 electrons in each atomic orbital, and we've got these subshell steps that fill up our entire shell. All right, so it's a little bit confusing, but let's take a look at what happens pictorially. And I'm not going to bother having you all copy this down or hand draw it. I'm just going to use an image directly from our book because it's simply a lot easier to do it this way. But let's take a look at the energy ladder. So these are the various energy levels for electrons. All right, so over here in the bottom, you can see if we have 2 electrons, we can definitely fit them both in this one shell. So I could say, all right, 2 electrons could go here, right? And then the next 2, if we've got 2 more, would go up into that next highest step, which in this case means we have to make this jump to subshell 2. So we'd be filling up the 2s orbital down here. And don't worry, I know this is really overwhelming. I'll show you tips for how to predict this. And then after that, we can jump up to this p orbital right here. And like I said, the p orbital is actually 3 different atomic orbitals. Each can fit 2 electrons. So our next 6 electrons could go here, and then we can keep on filling it up. The tricky thing, though, is sometimes we don't go straight up to the next shell when the lower shell is filled. And what I mean by that is, let's take a look at what's going on over here. So if you notice right here, that often the energy levels can overlap. So we'll just make a note that energy levels between shells can overlap. And what this means is that we may have to go, in this example, from our 3p orbital up to our 4s orbital, and then back over to our 3d orbital, meaning we're kind of zigzagging our way through this entire system. And like I said, I don't want you to memorize this pictorial diagram. It's completely overwhelming for most students. It's hard to know where they overlap, how they overlap, and things like that. But let's take a look at some ways that we can predict this. So I'll show you the tips that I use. So tips for predicting energy levels. All right, so I've got a periodic table image I wanted to show you really quick. And really, it's just your standard periodic table image. But what it's saying is that when we look at blocks 1 and 2a, these are called the s blocks, meaning they're made up of s orbitals. And in particular, we can start numbering these orbitals. So up here, I'd say this is going to be my 1s orbital. And then next one down would be 2s, 3s, and so on. And then over on this side, we've got our p orbitals. The one exception is right here. This s essentially is filling in that missing piece there, so just ignore that and remember that the top corner is going to be an s orbital. And with the p orbitals, we don't start at 1p, we always start at 2p. So it'd be 2p, and then below that would be 3p, 4p, 5p, and so on. And then over in the middle, right here, we've got our D block. Again, we're not going to start at 1. We're not going to start at 2. D blocks always start at 3 because they're the next highest. So we'd say 3, 4, 5, and 6. And the D block is always that transition element subset section. It's kind of recessed down into the periodic table. And then down in the very bottom, this is our F block that starts at 4F and 5F, and it is important to remember that the F block actually belongs kind of right here. So we show it below the periodic table, but it's actually a main part of the periodic table. All right, so let's go ahead and take an example element. So the example element I'm going to choose here is going to be carbon. So let's go ahead and block off carbon right there, and let's try to predict the orbitals that would make up the electrons in carbon. So let's make some notes. So carbon, if we look at it, is atomic number 8, which means that it has 8 total electrons. All right, so let's figure out what orbitals those electrons would go into. But it's pretty easy if we've got a scheme kind of like this. So we want to start out from basically the lowest spot on the periodic table and work our way up to carbon. So for example, I would go through the 1s orbital first, and I'd say, all right, 1s is going to be my first orbital. So I'd list that. And then once I go through, I kind of read it like a book, and I continue working my way through. And so I'd say, well, next, as we work our way down and left and right, we'd say it would be 2s. All right, and then over here, to get all the way to carbon, we have to go through a 2p orbital. Okay, so we've made it to carbon. We know that carbon has orbitals going up and through the 2p orbital, but it doesn't have the 3p, it doesn't have the 3d. We don't have to go through any of those on our pathway to finding carbon. All right, but now we need to go back to this other point, 8 total electrons, right? And let's make some notes, right? We know that the s orbital fits 2 electrons. Let me zoom out a little bit. And the p orbital, not orbits, fits 6 electrons. D orbital, if you remember, it has 5 atomic orbitals, which means it can fit 10 electrons. We can fit 2 in each atomic orbital. And for our F orbital, we can fit 14 electrons because it's made up of 7 atomic orbitals. All right, so again, going back to this idea, we've got 8 electrons. Let's fill them from lowest energy orbital to highest energy. So in our first section, I'd say I can fit 2 electrons in this first 1s orbital, but no more than that. So I've taken care of 2 out of the 8, so I have 6 left over. So now we need to go to our next highest orbital. Again, it's an s orbital, so I can only fit 2. So now I've taken care of my second orbital, and we've accounted for 4 out of our 8 electrons. But that still means we have 4 left over. Can we fit all 4 in this p orbital? Yes, because it can fit all the way up to 6 electrons. So this would be our electronic configuration for carbon. So I'm a big fan of using the periodic table kind of as a flowchart. The main thing is remembering the numbering system. So what I mean by that is, let me get my highlighter out. We start the s orbitals in the top corner at 1s. And then we start the p orbitals at 2p, and that's that main block over on the right. And then the 3ds are going to be a part of that middle block. And then the f's will start at 4, and they're the ones underneath. So if you remember that, you should be able to kind of work your way through the periodic table, almost reading it like a book. All right, I'll show you another trick. And some people prefer this other trick as well. So I'll say, or use this trick. And in this next trick, some people like doing it, but what I do is I start out with 1s, and then I just make a column, and I go 2s, 3s, 4s, 5s, 6s, and really you can stop at 7s. You don't need to go further. And then, like I said, the p orbitals start at 2, so I'm going to keep all the 2's in the same row, and I'm going to say 2p, 3p, 4p, 5p, and 6p. You can go to 7p, but that really doesn't even exist, so this is good enough for now. And then we can say 3d, 4d, 5d, 6d, and we don't really even need to go beyond that. But do you see how we've got all the numbers in the same row and all of the orbital types in the same column? It's pretty easy to remember how to make this. And then we go to our f's. Whoops, let me keep the same color. We'd say 4f, 5f, and 6f. Actually 6f doesn't exist, but let's just fill it in for fun. All right, so now what we want to do to predict orbitals are to fill in our diagonal lines. So first we go through 1s. I'd say, all right, we've done a diagonal line. Then next we go through a diagonal line that way. So we'd say it's followed by 2s. And then we'd say, all right, next diagonal line. We went through 2p, followed by 3s. And then we'd say, all right, then we go to 3p and 4s. And then next we go through here, which would be 3d, 4p, 5s, and so on. We can continue going through our diagonal lines this way. All right, so I hope that makes sense. You can use this to predict, but like I said, you can only fit up to 2 in an s, and you can only fit up to 6 electrons in a p. Sorry about my sloppy handwriting. You can only fit up to 10 electrons in a d, and you can only fit up to 14 electrons in an f orbital. So you can use either one of these tricks, but this is right here something you need to memorize, and I'm fine with you using any of these tricks on an exam. Okay, so let's do a few practice problems. And what I'll do is just pick some random elements and we'll try to predict the orbital filling, kind of like we did for carbon up here. But let's do it using a regular periodic table. So I'm just going to write down an example, and then I'll copy and paste over a periodic table. I'm a big fan of just writing on periodic tables, so it's okay if you want to print out copies of your periodic table and use them. I really don't care. I'm very much a learner where I have to write things down. I have to see it physically. So here's my periodic table. Let's go ahead and just pick one. Okay, so let's do chlorine. All right, so chlorine is going to be our example. And if we look at the periodic table, the elemental symbol for chlorine is capital C, lowercase l, right? So let's find it on the periodic table. Well, if we look at the periodic table, chlorine is going to be right there. Okay, so now we can use one of our tricks. We know that chlorine in this case is atomic number 18. Or sorry, atomic number 17, which means it has 17 protons plus 17 neutrons, or sorry, 17 electrons. If neutral, right? So we know that protons and electrons will balance out if we're talking about a neutral atom. Okay, so this means we have to account for 17 different electrons, and we have to know which orbitals they belong to. So like I said before, this whole block right here that I'm highlighting in orange is going to be my S block. So I'm going to say this is going to be 1s, 2s, 3s, and really we don't need to go on further because we know that the chlorine's going to be in period 3. All right, and then over here, we can say, well, this right here, this whole section over here is going to be our P block. And we said it starts at 2p, 3p, 4p, whoop, that's not the cleanest. I'm just going to write over this, 5p, and so on. Do we need to worry about the D block? No, but let's just go ahead and fill it in because why not? This right here is our D block, and I can go ahead and I can say that this starts at 3D, 4D, 5D, and so on. All right, if we want to go through, we can say, hey, down here, this is going to be our F block. And it doesn't start at 1, doesn't start at 2, doesn't start at 3. We need to go all the way up to 4F and then 5F. Okay, so now we've got our periodic table laid out. Let's work our way all the way over to carbon, okay? So I'm going to go ahead and just use a big, fat, thick red marker here. And I'm going to say, all right, we first need to go through our 1s block, right? So I'm going to say we must pass through the 1s block in order to get down to period 2. Okay, so let's go ahead and write that out. We've got 1s, and we can fit 2 electrons in that s orbital, right? And then next, we would say we need to go through the 2s block. Okay, so I'd say 2s, we can fit 2 electrons in there. So we're definitely not up to the 17, but that's okay. Let's keep working our way over. Now, as you can see, we've got this 2p orbital that we're going to pass through. So let's pass through the 2p's. Okay, so we've got our 2p orbital, and we can fit 6 electrons in that 2p orbital. So let me just go ahead and indicate that this is for chlorine. So we've got 6 electrons in our 2p. Now we're going to go to our 3s orbital, pass through that, and we can fit 2 electrons in there. And we can work our way all the way over to chlorine right there, which is in our 3p row. All right, but we need to make sure that we have the correct number of electrons, right? So over here, if we look at the number of electrons we put in 12. That means we're short 5, right? So in this case, we must have 5 electrons remaining, and those go in this p orbital. So this would be the proper electron filling diagram for chlorine. However, I'll show you a trick, and this trick is kind of unique. It basically says find the closest element in group 8A, or the last row. And so what this means is, let's go ahead and focus in on this section of the periodic table. These are called the noble gases. And what we can say is, let's just pretend like we're at neon. Okay, so over here, when we pass through this row, we also pass through the element neon before we got to chlorine, right? And neon, if we think about it, was basically this chemical configuration, meaning this orbital filling that I've got highlighted or boxed in red would represent neon. So what we can do is we can actually simplify this and basically say, all right, find the symbol right before and just change it to that halogen. So in this case, we could say chlorine, let's abbreviate this, would just be neon, and we'll put that in brackets, followed by 3s with 2 electrons, followed by 3p with 5 electrons. So you could write it this way as well. This is called the noble gas configuration. It just kind of simplifies things. All right, let's do one more. All right, and let's do this one underneath with a clean periodic table. So I'm just going to paste this one in. And let's do this, I don't know, let's do cobalt this time. So cobalt is this one right here. And like I said, if you want, you can just highlight your periodic table, or you can say that this is going to be, let me make this a little less thick. I like just writing in the margins, say 1s, 2s, 3s, and we know that it's in the 4th period, so I'll stop there. Whoop, that should be 4s. And then over here, I would say that this is 2p, 3p, 4p. And if you wanted to do the D's, you could say over here, this would be 3D, 4D, and so on. I'm not even going to worry about the F's because we're not dealing with that. All right, the closest element in group 8A over here on our pathway to getting to cobalt is going to be argon, right? So this atomic number 18 is going to be the one closest to cobalt, which is atomic number 27. All right, so let's go ahead and just quickly write this out. We know that cobalt, when we're looking at it, the closest noble gas is going to be argon. So I'll put that in parentheses. And then I'll continue working my way through the following row. So in the next row, we're going to go through that 4s, right? Because that's immediately what follows argon as we work our way down. So we can say that this would be 4s, and we can fit 2 electrons in there. And then next, we would work our way through the 3d column right there. So we'd say, all right, next up would be 3d. And if we count, I'm seeing 1, 2, 3, 4, 5, 6, 7 steps over in that D column, which means we would have 7 electrons total. So this would be the electronic configuration for cobalt. All right, I hope that makes sense. I know this is a little bit tricky, and I apologize that this video is a little long. But I did want to finish up by talking about 2 additional rules. And these rules are a little bit more nuanced, and it actually has to do with the orbital filling. So what I want to do is think about carbon. We already did carbon. That was one of our first examples. And we said up here when we did carbon that the electronic configuration was going to be 1s2, 2s2, 2p4. So let's just copy this down. So we said it would be 1s2, 2s2, and then 2p4. That was our electronic configuration for carbon. All right, if we wanted to do the same thing with our halogens, we could say, well, the one before was helium. So, or we could write this as helium, and then write 2s2, 2p4. So either one of these would be appropriate for carbon. All right, but let's think about what this looks like pictorially. So I'm going to draw my energy axis like that, going up and down. And then on the bottom, I'm going to say in this subshell, we have our 1s orbital, right? And then in our next highest shell, we've got our 2s orbitals. And the s orbitals we said are like spheres, and there's only one of them, which is why I'm only showing one atomic orbital for the s's. All right, next highest must be this 2p orbital, and the p orbitals are made up of 3 atomic orbitals. So I'm going to go ahead and draw it like that. Okay, so we need to start filling these orbitals with electrons, and we can fit 2 electrons in each atomic orbital. So I'll show you how I would go about doing this. For this first 1s orbital, we can fit 2 electrons, and we show electrons in chemistry with an arrow. So I've got a little arrow pointed up. The second electron that we put into that orbital needs to be spin opposite, meaning I'm going to put this as an arrow down. This is called the Pauli exclusion principle. And Pauli exclusion says that when electrons are paired, they are spin opposite. And it's kind of weird to think about, but electrons have a negative charge, and when they spin around, they actually make these little magnetic fields, and opposite magnetic fields are more stable than magnetic fields that are aligned. So in this case, we want to just try to create the energetically most favorable conformation, which is in this case going to be spin opposite. All right, so we've done 2 electrons out of our 8. Let's continue going up. So 1, 2, 3, 4, and we still have 4 left. So then the question is, how do we fill the p orbitals? Well, the next rule is we want to do 1 electron into each orbital before we start pairing any orbitals. So basically take up all the seats before you start pairing. And we've done 3, but we have 1 more, so we'll go ahead and do that 4th one over here. This is called Hund's rule. Let me clean up this R here. And Hund's rule essentially says that fill all orbitals in a subshell with 1 electron before pairing. All right, so this would be another way of kind of pictorially showing how these electrons are energetically filling. We have full 1s orbitals and 2s orbitals, but our 2p orbital actually has 2 atomic orbitals with single electrons in them. All right, I hope this makes sense, but let me know if you have any questions.